Welcome everybody. How's it going? How are you doing? How are you doing? How's it going? Tired. Oh. What's keeping you up? Nothing specific? Okay. I am asking you, yes. Yes. What was that? What? Oh, give someone else a turn. Okay. Well, it's great to be here as we wait for the. What happened here? Oh, of course. Why isn't it displaying? Because it's not connected. Okay, that should do it. All right, so today is an opportunity to discuss torsion, but before we get, and that's the wrong, this is torsion 9. Oh my goodness. All right. Okay, torsion. But before we get there, what are the administrative details for the class at this point? Yes, exam. All right. Exam is a week from today here. Okay.
Are we allowed to have like practice problems on it?
Practice problems. Yes. For example, if you go to the website, there are a number of exams.
I'm saying like, are we allowed to have those on our?
Oh yeah. Oh yeah. You can write whatever you want.
Okay.
Yeah, you can write whatever you want on the formula sheet.
I work best on like the problems backwards, if that makes sense.
Yeah.
So like.
Yeah. So on your 8.5 by 11 inch sheet of notes, you can write whatever you want. You can write examples. You can write equations. Okay. Please feel free to use that. It needs to be handwritten. Okay. It needs to be handwritten. Yes.
So you like print it out with handwritten like that?
So yeah, that's okay. Just don't make it microscopic, and do not copy and paste figures. I mean, you can draw figures, so just draw the figures that you need. Okay. The exercise is to help everyone create their set of notes. The content for exam 1 covers what we have through today. Okay. So session number 9 is fair game, and that is due, this session number 9 is due on Thursday, okay? What we cover on Thursday, session 10, will not be due on the exam date. That will be due a week from Thursday, okay? Yes, Daniel?
Do we get extension for the homework that will be on the day of the exam?
Yes, so the homework that is given out on Thursday is due a week from Thursday. The exam is on Tuesday. Okay? Yes? It goes through today. 9. It goes through today. Okay? Any other questions? Yes? Zach? Oh, okay. You're good. All right. Okay. So, so let's ask a question. How many people are still stuck on the finite element? You can be honest.
What?
How many? Okay, still some people stuck on the finite element? All right. Do you want to spend some time kind of reviewing that first before we do torsion? Or, okay, all right. So spit it out. What's wrong? What's going on?
My strain values are very strange.
Your strain values are very strange.
Positive and negative.
Okay. So in what respect? So the strain, are you talking in the latitudinal direction, or are you talking in the longitudinal direction?
The one we were, I forget the number, it was like, it was a 1-1 straight for one, like the
Yes.
direction we're
Yes. Okay. So
like the value for displacement was right, but the strain was wrong.
okay. All right. So first, did you calculate out what the strain should be? It sounds like you did, right? And so you've got a number here, and it's F over EA for the first one.
So, yeah,
Yes?
this was like last week, so.
Okay, okay. Well, you're telling me it's off, so I'm trying to get, so it's got to be off from something, right? Okay.
Like, so I got it, when I did it by hand, I got it right from the computer, like mechanics.
Okay.
Right,
Okay.
but it didn't line up with what the finite analysis was telling me.
Okay. When you measured the strain, where were you measuring it?
At the opposite end.
Okay.
Where the force.
So try moving over a little bit. Okay, because sometimes if you use the rigid body, okay, so what happens in finite element? All right. Often, okay, we have to constrain one end at a wall, right? And that's because we need to make sure all 6 degrees of freedom are not moving. Otherwise, if I apply a force, this thing's just going to accelerate. Okay, so what happens though is we have an idealized situation, right? In this case, it's idealized. Look, there's no constraint on the end. There's no constraint on the end. This thing is just in space. And so we've got the force over the area. We got this beautiful stress. The stress is uniform. La 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 la. Is that real? Well, in this fictional world, it is. Okay. In a real scenario, though, right? You've got to you've got to bolt it to the wall, essentially, right? So when you do that, what you have happening is at the wall, and if you applied a rigid body constraint to the right-hand side, like I showed, okay, what's going to happen is the material is not going to want to follow Poisson's ratio. What does that mean? That means at the walls, it's going to, well, the material would like to, I don't know if it has feelings, right? But it would like to to squeeze in, right? Because I'm stretching in this direction, so it's going to contract. But here, the material or the constraint is keeping it from being able to do that. So the measured stresses and strain that if you take a value at this end, they could be off. Okay? So what you want to do is you want to move over here, maybe right click, and do the query a little bit over in the middle region. Okay? And see if that does it. Where you want to take a snapshot, or you want to use a query where it's nice and continuous color, right? You'll see that there's often a gradient in color at the ends, okay? So maybe try that, okay? Other things. Was everybody able to at least create the mesh in pre-po max? Yes, okay. So then what else is going on? You can work on it now if you have questions. I'm okay with it. We're talking about it. Yes? What else? Any questions about the height? Question? Any insights into the height question for those that got it? So how do you calculate the change in height? Or the change in thickness of the beam that's being pulled? Yes? Yeah, using Poisson's ratio, right? So you can calculate it out, right? And you should have an estimate for what it should be, right? Using Poisson's ratio. Times the, right? So Poisson's ratio is the latitudinal strain over or the negative of the latitudinal strain over the longitudinal strain, right? So you can figure out how much strain you should have in the vertical direction, okay? And if I know what that strain is, and I need to know how much the thickness changed, right? I multiply by what the original thickness was. And that should be a negative number, okay? Other questions? Did anyone get it to work on a Mac by any chance? Okay, what was your trick to getting it to work on a Mac? Virtual machine. Okay, yeah, okay, right. Okay. Okay, should we go on then? Yes? No? Yes. Continue. All right. So torsion. And if you like, there are some formulas here that might be useful for normal loading. They're not all inclusive, but they're not bad. Okay, so we kind of skipped over we talked about shear strain. We didn't skip over it, right? But we kind of didn't have many questions on it. We've kind of been like, let's just worry about the normal stuff, and we'll get back to shear. Well, we can't avoid it any longer. We're here, okay? So we've talked before about how you have shear stress in Newtonian liquids, okay? And how essentially the force, like you can think of a liquid between two plates, and there's a force being applied on one plate, and it's causing it to slide with a liquid in between relative to another plate. Okay? In this case, it's not a liquid, but a material that we have in between these plates. And so we're looking at some displacement of this top portion. So you think this is the top plate, okay? This is the top of the plate, and this is some thickness, this dy, all right? And we have some delta displacement of the top relative to the bottom. Okay? And essentially what we say is this amount of deformation, all right, can be thought of, and again, it's unitless, right? Just like the normal strains were unitless. It's unitless, and it's actually this angle. So is it unitless? Well, like, are radians really unitless? Well, in our world, we consider radians essentially to be unitless. Okay? And this is, you think, well, no, you can't just say it's this divided by this, right? It's actually the tangent of this is equal to delta over dy, right? But we're talking about very small displacements, very small strains, so we can use a small angle approximation. So this is what shear strain is. And this is a simplified approach. If you look at the Wikipedia article on shear strain, you're going to see something that looks more like usually we say, okay, this is a nice little element. It's not actually that little. This is the dy. And then we say, okay, it's shifted over some amount. And then we have this thing like this. And we say, okay, that amount of shifting over is the delta. And then we have our alpha in here. And we say that we can approximate the I'm sorry, did I say alpha? Gamma. All right, gamma. Gamma as this, okay? And if you look, the people who really do this stuff in mechanics, they're like, no, that's kind of not the bestest way to do it. So what sometimes you'll see is that you actually start with an element that looks like a square again, but then the shear actually kind of does this, all right? And it does it on both sides. And then this angle is considered to be alpha. Sorry, I keep saying alpha. Gamma over 2. Okay. for our intents and purposes, let's just think of it this way. Okay. Now, just like we have Hooke's law for axial loading, right? We have sigma equals E epsilon, right? And we have other relationships that go further with the Poisson ratio, but we have a Hooke's law for pure shear. So we had Hooke's law for normal loading without transverse stresses, okay, or without latitudinal stresses, okay? And we have a Hooke's law for pure shear. So instead of sigma equals E epsilon, we have tau is equal to G gamma. All right. So in this case, all right, what we have is the ability to relate the shear strain to shear stress through a constant. And this constant, we won't derive it right now, but this constant, this is the shear modulus. Okay. So I guess maybe someone should write that somewhere. So we have shear modulus G. Okay. We have shear strain gamma. Okay. We can say that Hooke's law is tau G gamma. Okay, tau equals G gamma. And we can also make stress strain curves or shear stress versus shear strain curves like you see here. Okay, and it's very similar behavior. And this would be a ductile material because it didn't just pop. Okay, now that's a little background on shear strain and shear stress. What is going on and why are you going to relate this to shafts? Right? You're like, what? Wait, hold on. You just were talking about nice square and prismatic and rhombus looking things. Like why, how, what does this have to do with a shaft? Well, we're going to get there. First, if you have a shaft and you discretize it like this with a bunch of rectangles on its surface and there's no load, it stays like that. But once I've discretized it and I twist, okay, what happens to all these rectangles? Well, remember how we were just talking about boundary conditions and constraints in normal loading in finite element? Okay. In this case, if I constrain this end to the wall, all the points that are connected to the wall, or all these points that are right here on the edges, okay, of that, they have to stay in that location because it's constrained. Okay. But if I twist, if I apply a torque, right, so I have this end is attached to the wall. So everything here has to stay put. But then if I apply a torque, and yes, this is, let's do it such that you're using the right hand rule. Okay, so my thumb's now coming out, right, and I'm twisting like this. Look, all these, I can even keep it straight. We have those points that were initially along the same distance or along at the same height. That's not even right. At the same angle about the center axis, so like azimuthal angle, right? If I'm twisting this direction with the right hand rule, those same points start to go down. Okay, they move down, and we end up with a grid that is no longer nice and rectangular with right angles, but it has now a bunch of prismatic or rhombus-like looking structures. You see that? How these have moved? What does that look like? That looks like what we were just describing, right? We took something that had right angles, and now we've twisted it such that it no longer has a structure with just right angles. Okay? This is evidence that geometrically, we haven't even done any math yet, or done any math for this, right? Just looking at it, we see that there's some type of shear-like behavior. Now, when we get into this, and you can watch the video, what you see is that this, or a cylinder, a circular shaft, is kind of like a bunch of pizzas for multiple reasons. Okay, one, you can think I'm stacking a bunch of pizzas on top of each other. Okay, or pie, I don't know, whatever you like. It's a bunch of circular discs, okay, that I've stacked. And then I begin to look at a slice, right? So this is from a particular pizza place on campus, and this is a table on campus as well, all right? So I've got this stack of pies, and now I start to look at a piece of pizza on one of these pies, or between these two pies. What am I talking about? So if I'm applying a torque, all right, now the torque is coming out of the top. Let's say the torque is coming out of the top here. There's a torque, right? So it's twisting. And I originally had this nice kind of right angle setup, okay? So this is DA, and then actually this is a little bit different. This is not the same square that you see here, right? Or same rectangle that you see here. It's actually going in to the cylindrical shaft. And that rectangle here, okay, between the outer radius and some inner radius, rho, okay, is initially very nice and rectangular. But a couple things begin to happen. When I apply that torque, this point moves over here, all right? So you see if we call this A0, and now it moves to A1. So it's moved over relative to D. Okay, because we saw that behavior, right? We saw that behavior over here. Against the wall, these were pinned. But then we see things have to rotate, right, as we twist. So this motion, okay, of that rectangle from here to here results in a change out here that is actually larger than on the radius inside, all right? Because if you go all the way to the middle, if you go all the way to the center, there can't be any motion, right? And like it's like I'm twisting about the center, right? And so the relative displacement on that axis is 0. Okay? And so this motion from E0 to E1, all right? The E, this is going to displace a little bit less than, say, this A is going to displace when I twist. Okay? And A is going to move over more than D is going to move. All right. Any questions on this depiction? Okay. So, what happens? We're able to think, okay, here's a delta Z, right? My delta Z, all right? Here's Z, okay? Theta is this axis, right? And we're able to say, oh wait, there's an angle. Okay? There's an angle here. And it's an angle in what we'll call the theta z. Theta z is an interesting plane. Why is theta z an interesting plane? Because essentially, as I go around the perimeter, right, I have lots of theta z's. Okay? But what we see here is that this angle here, okay, has some displacement associated with it. And this angle, this arc of delta phi, okay, can be thought of as a radius, delta phi, for the product as being some displacement, delta here, and then there's going to be some angle here, and we know the height. This is describing, a shear strain. Okay. Dicey? A little complicated? Exciting? Okay. I got you on the first two in agreement, but maybe not exciting on the third. Okay? All right. So, what can we do? We can write an expression for the local shear strain as being that distance, this distance here, divided by the thickness of the pizza. Okay? So this is like, hey, how much did we have displacement? Like, how much did you move along the crust of your little slice of pizza, right? You see the pizza slice right here? Maybe I'm not. See, that's a pizza slice. Okay? And that distance, that the length of the crust, or maybe the inside of the crust, okay, is the numerator for our strain. That's a rho d phi, okay, because we can take the limit of as z goes to 0, and we can turn that into an infinitesimal small stuff, and then make this a derivative, okay, instead of just a delta. And this is the dz. Okay, any questions on that? Exciting, fun, boring? Great. Okay, so now we've defined a shear strain. And the shear strain, beware, it's dependent on rho. Okay? This is annoying, but powerful. If rho is equal to the outer radius, which we usually call c, okay? We will call a maximum, okay, when rho equals c, c is what we call the radius, okay? When it's equal to that, you have a maximum in the shear strain. When rho is equal to 0, at the middle, at the center axis of twist, that is going to give 0. Okay. And if this bar, okay, is twisting, or this shaft is twisting, notice that this d phi dz is going to be the same along this z-axis, right? So if I take it here, or I take it here, if I take it here, at least at a given radius, it's going to be the same. That's the strain, all right? But what happens with strain? Well, we've talked about how strain is equal to the change in length over original length, right? If I integrate all this up, right, I can figure out what the actual angle of twist is, right? The angle of twist here is not the same as the angle of twist here, but the shear strain here is equal to the shear strain here. Okay. So as you get a longer shaft for a given amount of torque, keeping the material constant, keeping the radius constant, do you expect for a given amount of torque more twist or less twist for a longer shaft? More twist, right? What is this like? This is like the springs we've been studying, right? This is like the bars we've been studying, right? You make the bar longer and you apply a given amount of force, and you get more delta, right? Yes?
Just so I understand it right, along that line, the shear strain is equal.
Yes, so along the z-axis, right, this is z, right, at a given radius, right, yes, the shear strain is going to be the same, okay? But the angle of twist keeps building up, okay? Now, we'll talk about angle of twist on Thursday, so that won't be on your exam, all right? But this is important. I think it's important to kind of have just a mental model of what's going on with deformation. You know, we're gonna get to a point where we have to put the state of shear stress on the surface of this thing. And what I come back to is what's happening with the deflection? Like, how are these rectangles deforming, right? If I twist this direction, then they're going to twist this direction. That means that this side is a little bit further down than this side, and then I can just draw the shear stresses like that. Okay, it makes life a little bit easier. Okay, so the there is a linear gradient, okay, of the shear strain as a function of rho. So we already said this, but this is now in math. Okay? If I'm at the center where rho equals 0, then I have 0 shear strain. But if I'm at the outer radius, I have the maximum shear strain. Now, we haven't said what the maximum is in terms of numbers. We're just saying there's a ratio. Okay? It's maxing out. We'll get that next time. Okay. So the other thing is, okay, we can think of a ratio of what happens, okay, to the angle of twist. Okay, it's still a ratio, not exact numbers, right? Not exact formulas, just a ratio. If I know that I have the maximum angle of twist at the end, phi of L will be a max, right? And I'm halfway there along this, then it's going to be half the maximum angle of twist. Okay. If I'm here, it's going to be, well, if I'm here, it's going to be 0. Here it might be a quarter, half, 3/4, full. Okay. All right. Now this is important. This is almost like, what's the parallel? Okay. What's the stress on a normally axially loaded bar? If I give you force and I give you cross-sectional area. F over A, right? Okay, we got that one, right? This is the equivalent for shear stress, okay, in a twisted shaft. Not quite F over A, not quite as simple, right? But this is kind of equal importance. Okay, so what is going on? We have shear strain, yes, wonderful, all right? Here is another wowie. Tau equals G gamma, right? And we've already been drawing normal stresses on elements. The shear stress is what causes shear strain, or shear strain often is a result of shear stress, right? At least for those cases where we have pure shear, okay? And there's no temperature business going on here, none of that, okay? All right, but that would be weird, okay? So we have shear stress, okay, like here, and this is positively defined. So they meet in the right corner and they meet in the left corner, in the bottom left. They meet in the top right and they meet in the bottom, all right? But what's going on? Remember how we said there is a gradient, right? We said that gamma is equal to rho over c times gamma max, right? We said there's a gradient. At the middle, there's no shear strain, and at the outside, there is a lot of shear strain, a maximum. We can now say that the same thing is true with the shear stress. Where there's no shear strain, there's no shear stress. And where there's a lot of shear strain, there's a lot of shear stress. Again, with ratios. Okay? And so what we have is this kind of interesting relationship where we can think of the shear stresses running linearly, okay? Just like we said we had before with a tau max and a rho over c indicating what tau at a distance from the center is. And then we say, okay, I'm going to think about what torque is. What is torque? Torque is the integral of all these little shear stresses acting on all these little areas on the face. And so I've got this little area and I've got this shear stress. If I had a force here and I had a radius here, right, you would say that's a torque. But I'm saying we have a shear stress on an area, on a little dA, right, and it's acting a radius, acting a distance from the middle. So that gives us a little microtorque. And we integrate, we add up all these little microtorques up, and then we're able to figure out what the torque is. Okay, so TZ, right, is the integral of all these TDAs, or tau DAs, sorry. Okay, times the radius associated with each of these little pieces. So we can figure out what the torque sums up to. We can do some substitution, and voila, we get an interesting relationship. We get this tau max over c, right, which we still don't really know what tau max is. All right, but we can say that it's equal to the integral of rho squared. All right, that comes out of here, rho squared dA. And this can be simplified and say, oh, this integral of rho squared dA is a very important quantity, which we call the polar moment of inertia. Okay, that's the definition of polar moment of inertia right there, integral of rho squared dA. And we then write tau max J over C is equal to torque. And that can be rearranged to say that tau max is equal to TC or tau TC over J. Okay. This is the formula you will want to have on your sheet. And the corollary is if I'm not at the max, if I'm not at the outer radius, if I'm at a rho, I know it varies linearly, and so the tau that I have along the radius in the radial direction as a function of radius, it's going to just be torque times rho over J. So I like to think of this, since we're in New Jersey and we have a wonderful neighboring school, this is TC and J. Okay? So TC over J. Now, if you want to think a little bit about what is the polar moment of area, okay? The polar moment of area is essentially, well, if we go back here, this is how much does the geometry affect the shear stress I'm going to experience. So if I have a larger, you kind of have this feeling already, right? That it's the integral of rho squared dA. So if I have a large diameter shaft, and I apply a given amount of torque, and I have a small diameter shaft, and I apply the same amount of torque, the stress is going to be, the shear stress is going to be higher in the smaller diameter. Okay? From here. It goes with rho squared, even though we have a C. Okay, this is a little bit counterintuitive, all right? So let's look at it. J, right, this is a rho squared dA, so it actually ends up going, if you do the integral out, it actually goes with c to the 4th. Okay? And the numerator has a c, so it goes with 1 over, the shear stress goes with 1 over c cubed, or radius cubed. Okay. Does this sound familiar? Shear stress goes with 1 over radius cubed. The maximum shear stress goes with 1 over radius cubed. Look, we did it. Supportable load, this is session 1. Supportable load scales with diameter cubed, or area to the 3/2. All right? We just derived it, because just like a material, right, just like we've talked about how we want to make sure that the normal stresses are below a certain level, right? We also are going to be thinking about how the shear stresses, what levels they need to be maintained at. And we'll get into some failure criteria to describe that. Okay? All right, lots of talking, lots of fun, hopefully. That's session 10, that's next time, sorry. Okay. Any questions up to this point? All right. Well, let's go ahead and do what some of you have been waiting for. And let's see. Oops. Okay. Okay.
Previous slide, just before this, there was a curling row and there's a row.
Yes.
Are they the same thing? Like a handwritten row? I'm not sure if that's density or just an arbitrary radius.
But we didn't do any process.
Typically, row is density. Right. And since it is inertia, I feel like that, like, it's easier to revise more or less. And this is.
Yes.
I had a question.
Yeah, hold on 1 second if you don't mind. Okay, so Kevin, so which one?
So, in the formulation for the polar moment of inertia, oh, they are the same thing. Okay, never mind. Yeah.
Yeah.
So, rho in this situation is an arbitrary radius, right?
Yeah. That's right. Okay, yes.
This is okay for this is for the second one. Because I thought that we
So you want to show the, I mean, yeah, it's okay. You want to show the shear.
That's
You wanna-
100%.
Not shear. You want to show
the dilation and the area.
yeah. So you want to show the epsilon 2 if you can. Epsilon 2 too.
Is that-
That's okay though.
Am I gonna get the 100?
I don't know.
No, come
Yeah,
on,
yeah,
don't
yeah.
do this to me.
So let me see. You're asking me to tell you what the grade is now, which is a little bit harsh.
Just yeah, I mean,
So
I have
what are
time.
you showing? So you show displacement.
Yeah, and since you gave us the sign, we can just multiply that.
Well, you have to know the.
And we're told that right here.
No. You want to know the.
Yeah, but like the facades gotta tell
Just
us.
add it. Just show the epsilon 2 and put it in the comments. Submit a comment. Just put the epsilon 2 on your board. Show the epsilon 2. See, that's
That's like the.
that's the vertical.
I mean, I already. Like I already submitted it.
Yeah, that's what I'm saying. So add a comment and say, here's
I did
my,
it correct though.
that's great. I have to agree that part still. There's no points for that part. Look, that's 2 points. Okay. Yes.
that?
No, they were first.
Oh, okay.
Sorry.
Sorry about that.
I just want to double check, you said session 10 was not going to be.
That's right.
And, we have the whole.
Yes, why don't
I
you?
accidentally.
It's okay, just put a comment. Finish the comment.
Okay, my bad. Sorry.
But I forgot. I did run like a simulation and have like it shows like why is that and actually you can take the numbers and
That's the same, and it's, you know, it's the same thing with top.
You say for the day, where is response to
For a circular process. Because we integrate, I mean, it's, what I did now, right? We integrate from and we're integrating So, good catch. Right, so this should be. So, we're using the same location. And so, and I think I'm self-consistent. So, this is the location I suggest. Alright? Alright. Yeah. Yeah. Yeah.
when the side's out, it's gonna look like. Yeah. Or like under it. It's just there is an option. But I feel like they'll look at me as like I feel like there would be a lot of
So the game plan for this, I should take sections and analyze it to work on like each section. That's correct. So like even so here, I didn't get to this point, right, today, but see, remember how we could say, okay, if we have a torque on one side, we have a torque on the other side, and then we can say, okay, well, they're gonna be equal to each other, right? What gets tricky, right, is when you say, okay, I'm gonna take a slice of that shaft, and then I need to define an internal torque, right? Because just like
Interesting.
when we calculate, stress, we're talking about what's the internal force. Right? Here we're kind of the internal force. Okay. So when we do that, that's when you have this, and so now you can say, oh well, TA is equal to TAB. Right? It gets a little bit more complicated when we have
That middle section right there, like B to C.
yes, right. So here, right, if I take so TAB, right? So that's straightforward, right? Because that's just going to equal to T. TBC is actually pretty straightforward too. If you slice here and you take off the left, right, then all I have is the 2T over 3 on this side. So the internal torque has to be equal to 2T over 3. Alright?
I think I see where you're going.
Okay? So that's what you have here. That's what this diagram is.
This is representing A to B to the section right now.
This one is. This is TAB is this.
And just to be absolutely sure,
And
AB represents the internal force, correct?
internal torque.
Yes,
Yeah, well, the torque in between these two that the shaft is experiencing. Yeah. And then TBC is here. And now I'm opening up this space. Okay? I'm defining that to be positive, right? Using the right hand rule.
What was the question?
Using the right hand rule, right? That's going in. This is coming out. Right? That's the torque, TBC. And then I have defined 2T over 3 on the right side. Okay, and why does this all work? This all works because these are external torques and they have to sum up to 0, right? Because that has to be an equilibrium. So just like we do the other concepts, first I want to do external equilibrium, which I did. You don't have to do it. Okay? Because like I said, this is T is T over 3 is T.
Yeah.
Well, you want to check, right, that those 3, right? Because this is, if you say, okay, if I'm going to say, it depends on which side. When you do external, right, it doesn't, you just got to pick a way. So if I'm going to say this is T, and this is minus T over 3, and this is minus 2 over 3, like that would be coming out this way.
I understand what you're saying. Okay. So, game plan, you already did the first external equilibrium. Well, the external equilibrium, that's done.
Right, that's already done.
Our next step, we would take slices and divide it into sections and do sum of forces equals 0 again.
Yeah.
Then we're gonna deal with internal forces.
Internal torques, yes.
Yes. And from there.
And then from those torques, then you can figure out what the shear stress is using TC over J. Yes, question?
No question.
You understand any better now?
Yeah, I think so.
Yeah.
Okay. Good. Questions? Any questions? Up there, okay.
See, that's why they're because then I call no, it's gonna retract like that's all. In that case, this can't make it. This box and then there's things going in and also when you're in, like, so many wires and like get caught up inside where you're like,
Yeah, we know.
yeah, this one's too complicated. I needed to talk about this with someone because it's good. Like, I don't know if I'm right? Okay, how is that rotational?
Right? So that's the way, right? Real is tackling in the line for opposite. Okay, so we've got A, so first, what is
What was that?
so we gotta figure out what 2D is. So what is 2D? I agree. I agree with that, okay? This is because okay, so now, let's write that, if I was right, we're gonna do, TC over here. So this T is 2T over here. Okay, C, what is C? True. Yes, yeah, so that would be 1.1. And yeah, you're right. So we got a T row. But we gotta calculate it as well, right? Yeah, so that's where things are in place. So you don't want to use row when you calculate it out. J is the higher line. It doesn't care about A. So J is going to be here. Yeah, the radius is 2x. So you need to know the C, and you know that. Then row you got twice, essentially on the quarter. So you're going to do that. That's right before. Alright. Okay. Yeah. Well, you kind of scale it quite a bit. Well, yeah. You mind if I touch it? So. Okay, so, whoa, alright, so maximum size, okay, so this is pretty big. Okay, so let's start. This is not the right one. No, okay. Okay, yeah. You move the file itself into another directory. Hold on. Yeah, I mean, because I saw stuff moving around here, so, I just beat down my name, we got it, try it down. I don't know what to say, that here. Yeah. So, previous, the entire. Okay, so when you do planning on the house. You have, right, 1 hour. All the For those of us who are not from serious, what we can is after you've done the work, and not very many elements. So, and we set the maximum element size. That's right. You can create an element larger than that. Okay, and that's from 4 to 6, you make a lot of elements. Right, you increase that maximum element size. Then it's going to, it's going to try to push that down. Right? So it's really the max. And then you have 2 elements, and you're not good on that. Yeah. I mean, it's like, you can make it different, and what's cool is typically your, simulation. So if you're doing like a really detailed and needed to be highly accurate analysis, so we usually start with a low range and then you calculate out. And then you calculate out. Increasing, and then you show that the value that you calculated is equal to the root of that. Probably unlikely. Well, yeah. Yeah, but it actually, there are other problems. But we can use squares and rectangles and stuff, and we will show some stuff. But actually, the math, the mechanics are most accurate. So, yeah, you really can get away with it. Now, if you, and what we will talk about next time is the equivalent of our food, right? Remember how there's an example? C, E, L, for EX, EX, over EA. Yeah. Right. This is due to what we have on Thursday, we do Thursday. Yeah. So you okay, all right. So there's 2 things that we have to do. This is great that you there's 2 things. One, and it's not in kilograms of force, it's actually in kilograms of force and contact. Okay, so you've got a force, right, that is essentially a force in a radius, and you've got a force which is not a force in a radius. So those, you don't say this force is equal to this force, you actually say this force is equal to this force. And the radiuses are different. Yeah, so the gear ratio helps you with that, right? The other thing is the person that you the next thing is that you have ability for So those are the two things you have to count. Equilibrium forces and displacements. Okay, and I better help others. Yeah. What's up? Okay. Okay, yeah. Okay, so cancel. So under section, right? So you gotta put the part. And yes, now that should do it. No problem. That one was an easy one. No charge.
Question that makes sense of applying the idea of the displacement of the center line. Like I understand how you use geometric patterns to arrive at this thing, but I'm not sure what the extra step I need is to find the change in that center line.
Okay, so if you go through on a map, right, you can figure out, I think like this is in those examples, what your strain is in the first region and strain is in the second. If I want the strain, if I want the displacement to the right, and I know the strain of this side, I know the strain in this region. The strain in this region, what it does is the strain. Okay, yeah, so probably say it's the delta L over L.
Is like the reaction by the second one?
It's gonna be, you take that strain and you multiply by that plane, it'll be the negative. Because for geometric compatibility, right, this, yeah. There are two ways to do this problem. One is using superposition, the other way is using the compatibility, right? Both will get you, and I don't think you can do it, both will get you the strain in both regions, right? And once you have a strain there, the strains are not necessarily associated, right? But the displacements add together. So the displacements we were going to be at the intersection.
So just to clarify, when you're looking at each of these strains,
Those are displacements. Yeah. Yeah.
so you have to compute F and then run that through to find those.
That's right.
Okay.
If you use this is the case.
So the reason that's the case is because the two things that are impacting your displacement are thermal expansion and then your strain.
Very good. Okay, good luck. And your name again is?
If I'm unable to go to office hours on Friday, can I email you?
Yeah, you can. But don't send me canvas. It's for your own benefit. It's much more likely that I will answer if it's through Canvas than if it's through email. Yes. And okay, your name is? Okay, great.
Yeah, they have like the weird shit. Like I thought like the like it's like so weird. Well, yeah, right. They make jeans, so then I think they also just make shirts. I don't know, like yeah, they probably find out if I have
swing cutting. So this question, and this is half of it. It's about like three. So what is C? That's my mistake. Yes, C is actually gonna come from 5. Right, and C is the radius, and that's coming around. Right. That should be right as long as you got the relevant C. Okay, good luck. Okay, yes. Okay, great. Okay.
So like, minus.
Okay, yeah. I don't think, yeah, I mean, you just hold it. Yeah.
How would you?
You don't have to.
That makes sense.
So let's go ahead and figure it out. And scale it down. One month out.
I read it like 5 times. I just.
All right. Good. Okay, so now we'll do that.
You're thinking about the Bears like.
Okay, now I'm gonna some parts. Okay, now this number is too high, so we'll just put in 0.00.
By the way,
Here. Okay. So now we create. Okay, so how do you create the SDL?
oh, we're not gonna ignore history. We're gonna say it, and we're gonna explain.
I guess it makes, it's like, I guess they're owning up to like, I guess you shred it, make this goes down to this whole direction. So.
So we're on page 8. And this is 130, yeah, 13. Okay, that was. It's like, where's the file? Yeah, so we're gonna try a different I just created geometry from scratch. Where is it? It's in your downloads. Yeah. Something happened. Whoa. Did it download? Yeah, did it extract? That's weird. Well, something weird is happening. Maybe the default for now. Let's see what happens. This is a regular Windows PC, right? Yeah, maybe try re-downloading to your Mac, because something that's happened in the settings, like it's saying this stuff is changing, and I don't know what happened, but yeah, I tried re-downloading and. Try again, wait, I actually can't, oh, I don't know why, I have reset it, I don't know why it's not even letting us do it. So something didn't happen. That way, it won't be 2 layers, it's like 2 layers deep. Yeah, it's somehow running in the background. So anyway. Okay, you saw that, it was like, it was somehow running in the background, which is not good. Okay, now. Let's try it now. Yes, is there any more info? But anyway. I don't know. But it was something that got corrupted internally, all right? Okay, so now you want to go through all the steps, all right? That's just a mesh, right? So go through the video, all right? You can't show the strain until you've loaded it properly, okay? So why don't you go through, I mean, all right. No, that's fine. Okay, so, I mean, we want to have this work, right? So we're gonna define the material. It's gonna be your last grade. And I can't, what was the, 161 gigapascals. You just say 2, 3, okay? And then a bit of a song ratio. So for this, we're going to define the section. We're going to do the section off the part. And we're going to select this all section. Then we're going to do the static step. That's not very much other stuff. Now, centimeters long. So we're over there, actually 11 centimeters, and then the X was the width was 1 centimeter, and the height is 2 centimeters, so we're gonna cover here. Half that, so 1 centimeter. 5 centimeters. And this is going to be okay, so that was right there in the middle. Okay, and for the and we're going to make the rigid body. We're going to use it on a surface. It's going to be this surface. We'll make that vertical. What is that? Okay, now what we're going to do is verify the load. Take a load, we're going to use we're going to use it on reference point 1. And now that's what we're now going to put in my load. So essentially that's going to be the one direction or the one direction.
Yeah, but what am I gonna do? Take it.
Well, this is
the niche inching class.
screen that is height and multiply it by the height. Okay. So here we should be ready to do the analysis. We should move it here. We do the analysis around this. And then we look at the results. Okay, and then we come over here and we're going to come and look at the strain. And it's the epsilon 1. So then we do look at query, you write, you do query, and it tells you that's a string. Okay, alright, and so, now, we also, for the next one, what you can do is you can figure out what this is string in this direction, right? In the direction, we need to do string in the y direction. So to do that, we go to E2, and it's going to be negative because it's pulling this way and it's shrinking in that direction. When we want to change the length in that direction, you take the strain, right, and you multiply by that, and that's a negative number. All right. Good luck.
You mentioned yes, someone is joining us in the meeting tomorrow.
What's that?
You mentioned on Teams, you mentioned some guest.
The seminar speaker. Just for me. I had to meet them.
So he will be, to show him the designs.
Yeah.
Okay.
Yeah.
I thought there's someone from NC State joining us in person.
Yeah. Then we have the NC State meeting tomorrow too.
No, I was thinking like someone from NC State.
Oh no, not that. No.
And for the assignments, like there are many questions which ask to upload the image. So do I have to grade it? Okay.
Thank you.
Yeah, like a couple of students asked